All right, let's jump right in. Today, we're going to cackle two concepts from graph theory that sound almost identical, but trust me, are worlds apart when it comes to how difficult they are: Eulerian and Hamiltonian paths. So we're going to explore this exact question. Why is one of these a fun little puzzle with a simple trick, while the other is a monster of a problem that can bring even supercomputers to their knees? By the time we're done here, you'll get it. Okay, so here's the absolute core of it all. It boils down to one single word: edges versus nodes. An Eulerian path, that's about traveling over every single edge. Think of it as every road in a city. A Hamiltonian path is about visiting every single node, like every landmark in that city. That one little difference, it changes absolutely everything. So here's our game plan. We're going to break down each path, take a look at some really surprising ways they show up in the real world, and then we'll wrap it all up with a super focused study guide to nail this for any exam. Let's kick things off with the easy twin, the Eulerian path. You know, this whole area of graph theory pretty much started right here, when the great mathematician Leonhard Euler solved the famous Königsberg Bridge problem way back in 1736. The goal is super simple, right? Think of it like those trace-the-picture puzzles from when you were a kid. Can you draw the whole thing without ever lifting your pen off the paper and without ever going over the same line twice? If you can, boom, you found an Eulerian path. And this is where it gets really cool. There's a magic rule. You don't actually have to try and draw it out. All you got to do is count the degree of each node. That's just how many edges are connected to it. If every single node has an even number of connections, you can make a full loop, a circuit. Or, if exactly two nodes have an odd number, you can draw a path, starting at one and ending at the other. That's it. So on an exam, this is your secret weapon. For an Eulerian problem, do not waste a single second trying to trace the path. Just go to each node and count the lines coming out of it. It's a brilliant shortcut that turns a tricky drawing puzzle into a simple counting exercise. All right, so that was the easy one. Now let's move on to its much tougher twin. This is where our fun little puzzle suddenly becomes a massive computational problem. Now the goal here, totally different. We don't really care about the edges anymore. We don't have to use all of them. Our mission now is to visit every single node, every landmark on our map exactly one time. And here is the kicker, the big twist. Unlike with Eulerian paths, there is no simple rule. No magic trick for counting degrees, nothing. The easy shortcut is just gone. Finding a Hamiltonian path is what we call an NP-hard problem. So what does that really mean? It means for any decent-sized graph, the only way to be 100% sure if a path exists is to try every single possibility. This brute force method just isn't practical. The number of paths to check explodes so fast that even the world's best supercomputers would give up. Now hold on. While there's no easy test that works for every graph, there are some special conditions that give us a guarantee. Theorems from guys like Dirac and Orr basically tell us the same thing. If your graph is super dense, just jam-packed with edges, then you're guaranteed to find a Hamiltonian path. Okay, so why should we care about all this? Is it just a bunch of abstract math puzzles? No way. Turns out, these paths have some seriously cool and unexpected applications in the real world. Check this out. Imagine you need to create one single, super compact string of code that contains every possible 3-digit binary combination. How would you do it? Well, you can actually use an Eulerian path to build it for you. So this little 10-character string right here, it's called a De Bruijn sequence. It looks kind of random, but if you take a 3-character window and slide it across, you'll find every single 3-bit combo in there. 000, 001, 010, all of them. It's generated by finding a Eulerian path in a very cleverly designed graph. Pretty neat, huh? And now for our hard twin, the Hamiltonian path. You've probably seen this one before, even if you didn't know its name. It's the classic Knight's Tour puzzle on a chessboard. The challenge? Get a knight to land on every single square of the board, but only once. Since this is an NP-hard problem, there's no simple formula. So what do? We use smart strategies, or heuristics, to help guide us. Warnsdorf's rule is a perfect example. It's a simple idea. Always move the knight to the square that gives it the fewest escape routes for its next move. It's like trapping yourself on purpose, and counterintuitively, it works incredibly well to find a full tour. Okay, let's pull all this together. If you've got an exam coming up, this is the part you really want to lock in. This is your cheat sheet. This table right here, this is everything. If you remember one thing, make it this. Focus. Eulerian is edges. Hamiltonian is nodes. Analogy. Tracing all the roads versus visiting all the landmarks. And the big one, the test. Eulerian is easy, just count the degrees. Hamiltonian is hard. There's no simple test. And here are your final revision tips. For any problem that smells like a Eulerian path, your very first move should be counting node degrees. For Hamiltonian, just accept there's no easy way out. And please, please, please do not mix them up. Edge versus node, that is the #1 mistake people make, so burn that difference into your brain. So it's pretty wild when you think about it. One tiny change in a rule, tracing edges versus visiting nodes, separates a puzzle you can solve in seconds from a problem that pushes the very limits of what we can compute. So the next time you see a simple problem, you gotta ask yourself, is this an Eulerian path with a clever trick? Or is it a Hamiltonian path, the tip of a much, much deeper iceberg?